Hello, guys. I hope wherever you are and whatever you're doing, you're well and you're safe. So, before I start talking about the dynamics of rigid bodies and how can we analyze forces and torques applied to a rigid body using kinematics and kinetics together, I wanted to talk about something else in this class. I want to talk about moment of inertia. So moment is not a new concept, right? Moment of inertia, you have seen this before in statics when you were studying areas and how to find the centroids for different surfaces. You've dealt with first moment of area, second moment of area, or moment of area, moment of inertia, or just moment of inertia. People refer to them in different ways depending on who you talk to. Um, so, in engineering, let's take one step back and think about what a moment is. So, in engineering, and how does the concept of moment relate to uh, moment of inertia? So in engineering, when we talk about moment, obviously in most cases we are not talking about a specific moment in time. We are talking about, if I want to loosely define it or explain it, we're talking about something that makes an object rotate, right? When you apply a moment or torque to an object, we try to rotate that object. We try to rotate that part or rigid body. So let me try to put it this way. So a moment in engineering, we are basically talking about. Let me just put that loose definition. Something that makes an object rotate. Or at least we want that object to rotate when we apply that uh, when we apply a torque or a moment in that object on that object. Now let's see if we have, let's say, a piece of metal or a beam. Just going to try to put something simple here, and we want this to rotate. Let's say we apply. If it's the center, we want it to rotate around the center. We apply some forces, force here, force there. We apply a torque to this, apply a moment to this, and it rotates around the center. Right? That's a moment, or in a better way, um, moment or torque. That's what we want. That's what we apply to an object to make it rotate. Now, in mathematics, though, they define moment. Well, it's mathematics, so it's more theoretical, less related to physical concepts. So, in mathematics, they define it using an integral. If you talk to a mathematician and you talk about the moment, let me put it this way. In mathematics, we define a moment as, let me just say this, an integral. Let me write it first. X minus c over n fx dx from minus infinity to plus infinity. Now, looks a little scary, but this is not something again new. You have seen this before actually, but in engineering. So this whole integral is nothing but what it's trying to say is we have a function fx, and that function is multiplied by some distance. This x is just distance, c is just a constant number, so x minus c is just a distance. So it's a function multiplied by a distance raised to a power n, and then they integrate it from minus infinity to plus infinity, or whatever the domain is. Now, let's see where we saw this before and how does this relate to the concepts that we have in engineering. So let me just do this. Now, let's start with when the power is 1. When n is 1, so when n is 1, we say we have first moment. It's first moment. Now, what is first moment? First moment, actually, again, you've seen it before. It's nothing but the first moment of area in engineering, using the same equation that mathematicians use to define a moment. If you remember when we were trying to find the centroid of a shape, let's say we have a shape like this. I'm just gonna put it right here. Let's say we have a shape like this. These are axes. This is fx, this is x, and then we have some function, some random function, and we are trying to find the centroid. And let's say the centroid is somewhere here. I don't know where it is, but I'm guessing. So somewhere around there. How do we find the centroid of this shape, this random shape that we have its equation, or we know how it changes over x? We were just defining the centroid as the centroid, or x bar, where the center of this shape is the integral from 0, let's say it starts from 0 and ends in xf, to xf, x fx dx over from 0 to xf fx dx, which is this is basically the area. Now this is nothing but this equation, this integral. Changes from 0, well, it starts from 0, so we have the limit from 0 to xf, where it ends, and then we have a distance, right, raised to a power, its first moment to the power is 1, multiplied by a function, fx, whatever the shape is. And this is the first moment of area. You have seen this before. Right? This is, let me see if I can put it there. This is the first moment of area. Now, what happens if we increase n? What if n is 2? So when n is 2, we'll get the second moment. Second moment. Where have you seen this? Well, when we calculate the second moment of area. If we have a shape like, let me bring a simple shape here. Let's say we have something simple. Just a rectangle. So we have some shape like this, and here are the axes. This is, let's say, the x-axis, and this is the y-axis. This is x, and let's say this is the cross-section area of a beam. You've seen it in solid mechanics course. This is the cross-section area of a beam. So when we want to calculate the second moment of area, I, for this beam, we had the integral y squared dA, and this integral was over the area. Right? It's a double integral, basically, because we're integrating over area. And this is nothing, again, but the definitional moment. This is the distance raised to a power, in this case is n, n is 2 because it's the second moment, multiplied by a function. Function here is just 1. So it's distance raised to a power multiplied by a function. Right? This would be, this is we have seen before. This is second moment of area. Moment of area. Or moment of inertia, depending on again who you talk to. Where you have seen this when we were using, when we were dealing with bending in beams. If you remember, for instance, Euler beam, we had, if I remember correctly, the equation was something along the line that EI was EI d4y dx4 is equal to some shear force. Right? We had this in solid mechanics. E is the margin of elasticity. I is the moment of inertia or the second moment of area. This is the fourth order differential equation. Pretty much the whole thing. And Qx is the shear force applied to beam. So that's where you've seen this. This is second moment of area. This comes from the same definition, right, for the moment when n is equal to 2. So these are what you've seen before. Now I'm going to introduce something new, a new type of moment, moment of inertia for a mass. So here we had it for the area. Find where the centroid is, center of the area is. Here we had the second moment of area, and it's nothing but the concept is nothing but the stiffness because of the shape. So we could find it in either direction. The higher it is, the stiffer the beam is in that direction, and that's why we're using it when we're dealing with bending beams. But that's something related to solid mechanics and that course. Now, what is the mass moment of inertia then? If these are this is the moment. That's how we define moments in terms of mathematical language, and we saw the applications in before. This for n1 equals to 1 and n equals to 2. Let's take a look at mass moment of inertia now. This is a new concept related to this course. And let me go to the next page. Now, the way I want you to think about the mass moment of inertia is that think about, so before we were talking just about objects and particles, right? We didn't really care about the shape of the particle when we were talking about just particles, and we were focused on how can we analyze the motion of particles, the dynamics of particles. Now we're dealing with rigid bodies. So one of the differences between a particle and a rigid body is that the big difference is that, or the main difference is that a particle doesn't have a shape when we are studying that. When we're studying a particle, right? We don't care about the shape. But when we are dealing with a rigid body, we really care about the shape and how the mass is distributed, right? And there is a reason for that. When we have a rigid body and the rigid body is subjected to a couple of torques, moments, forces, couples, we are going to have a rotational motion, right? We talked about the kinematics. When we were talking about kinematics, we said we have a specific kind of motion when it comes to rigid bodies, and it's rotation about a fixed axis, or some kind of motion that has both translation and rotation, which is more like a general motion of a rigid body. So when the rigid body is subjected to forces and it has some rotational motion, that motion depends on the mass of the body and how that mass is distributed. So it's not just about how heavy the object or the rigid body is, it's also about how that mass is distributed in the volume of that body, so better to say, what is the shape of the body or the rigid body, and how does the mass is distributed in that shape. So let me write it this way. Mass moment of inertia. So when A rigid body is subjected to forces and I would say couples. The rotational motion, the rotational motion that results, we're going to have some kind of rotation if the motion is not just a translational motion. The rotational motion that results depends not only on the mass of the body, but also how it's distributed. But also how let's put it this way, how the mass is distributed. This is very important, how it's distributed. Now, the way I want you to think about it is that think about a basketball. When you have a basketball and you want to rotate that basketball, let's say you put it on one of your fingers, so you're a pretty skilled basketball player, you put it in one of your fingers and you try to rotate that ball around the axis that passes through the center of the ball. It's a relatively easy job to do. Right? You just have to slightly give some force to that ball to make it rotate around that center. Let me see if I have, I do have it here. So let's say you have a basketball and you are trying to rotate that ball around its center of rotation, or somewhere here. Probably it's not exactly in the center, what I draw, but except, right? You put it on your finger and you try to rotate it around the center. It's a very easy job to do. It's a very easy job to do. You don't have to do that much. You don't have to apply that much force to the surface to make it rotate. Now, the same basketball, think about it this way, that you are holding it away from your body with both hands, or one hand, doesn't matter, and you're trying to rotate the ball around yourself. Imagine that your body is the axis of rotation and you're trying to rotate it around your body. So if I want to show it, what I'm trying to say is that, let's say this is the axis of rotation, which is your body, and you're holding the ball at some distance, I guess far as your hand goes, and you're trying to rotate it around yourself. Now, this is a different case. If you try this, you will see that you need much more force to make this rotation. The ball is the same, has the same mass, but now it's farther from the axis of rotation. So it's not just about how heavy the ball is when you want to rotate around an axis. It's also about how far the ball or the rigid body is from that axis. The farther it is, the more force you need, the harder it becomes to rotate that object. So if you want to define mass moment of inertia, let me put it this way. If I want to define it, I'll go with this. I say mass moment of inertia is the resistance of an object to rotational acceleration. When you want to accelerate that ball, right? The farther it is, the harder it becomes. So the resistance of an object to rotational acceleration about a particular axis. That's how I define moment of inertia, or mass moment of inertia. So the resistance, the resistance of an object to rotational acceleration. You want to accelerate an object around an axis about a particular axis, that's it, about a particular axis. So how hard it is to make an object rotate about an axis. Now, what it is, in other words, it's nothing but the rotational equivalent of mass. What was mass? Mass was the resistance of an object to linear acceleration. Right? When F equals to ma, when we wanted to accelerate an object, the heavier that object was, F equals to ma, the heavier the object, the higher the m, more force you need to accelerate that object. Now in this case, let me write it this way. It's the rotational equivalent of mass, right? Newton's second law for a linear motion, we had summation of forces applied to mass is equal to ma. Now in this case, we have summation of moments is equal to I alpha. So this is for rotational motion. We'll talk about it, talk about this much more later on when we start studying the dynamics of rigid body. But I is the moment of inertia. Unfortunately, they use the same notation for mass moment of inertia and area, second moment of area, or area moment of inertia. That's how it's always been. I know it can be confusing, but what you can do is later on I'll explain that a little bit more. You can look at the units to identify or differentiate which one we are talking about, or which one the problem or the situation is talking about. But so mass is the resistance of an object to acceleration. The higher the mass, the higher the force you need to accelerate an object. Moment of inertia is the equivalent of mass in a rotational motion. So it's a rotational equivalent of mass. Is the resistance of an object to rotational acceleration. So the higher the I, the higher the moment you need to accelerate that object, right? Angular acceleration. Now, let's look at it like a rotating disc. Let me see. Let's my handwriting for some reason is getting worse. Let's look at a disc rotating about its center. And looking at a small element of the disc, let me bring this, or at least make something similar to a disc here. Let's use this. Let's say it's a disc rotating around its center right there. Let's say it's rotating this way with some angular acceleration alpha. Now, looking at a small element of this, let me see. We look at just the small mass element, just this mass, and it's at some distance r from the center. Let me see if I can make it a little more visible. So this is the distance of that's some element, a small element of this object, of this disk, rotating disk. So looking at a small element of the disk, I can write I can define mass moment of inertia. Integral r squared dm. It's a second moment, distance squared times some function. And take this integral, integrate it over the mass, for the whole mass. So we just have a small element. If we calculate this integral over the mass, we can find, imagine that this disk is made up of so many of these small elements, right? There's another one. Let's say we can have another one here, another one here, another one there. You have so many elements enough to cover this disk. So you're doing pretty much, you're taking this integral over the mass of this disk. This gives you the moment of inertia. This is the general equation for a moment of inertia. Let me define the terms. This is I. As I said, we use the same notation that we use, or same letter that we use for area moment of inertia. So this is second moment of mass. Second moment of mass, or mass moment of inertia, or moment of inertia. Mass moment of inertia. This whole thing, what is this? This we have seen, right? This is the definition, mathematical definition of moment. This is the moment when n is equal to 2. So that's distance squared times some function. I'm just going to erase it. This is distance squared times some function. So this is what we are introducing now as a new concept related to the rotation of a rigid body. Now, if I want to wrap this up, you can think about it, these moments this way. So the area moment of inertia and mass moment of inertia. Area moment of inertia was what you knew from before, from statics. Mass moment of inertia is something new that we introduced, right? Area moment of inertia and mass moment of inertia, both are second moments. Mathematically speaking, there are some distance squared, n is equal to 2. Both are second moment. However, area moment of inertia is with respect to geometrical area. Area moment of inertia is with respect to geometrical area, and mass moment of inertia is with respect to the mass of an object and how it tells us how it's distributed. We basically take into account the distribution of the mass for an object.